Great. Thank you very much for coming to attend our presentation. My name is Megan Farrell. This is Christopher Ling. Outside at our booth, you can meet Andrew Boudou and Jackson Ellard, who will be equally happy to discuss our material with you. We're really excited to come here and present to you on lithium-ion batteries and the aerogel anode that we hope will lead to significant parameter improvement in the future. We'll take a very linear path through our presentation and talk about what we see the future of lithium-ion batteries as progressing towards, our proposed treatment of the problem, how we numerically attempted to quantify this, our aerogel fabrication process, characterization, coin cell fabrication, and finally validation and testing of our design. And we'll talk quickly about what that all amounts to and how future work could attempt to commercialize this product better. As we all know, lithium-ion batteries have very high specific energy. This has really meant that they've largely taken over almost all battery applications, whether these are automotive or small portable power sources. Their energy for their weight simply can't be beat. Because they have limited charge times, however, the applications that they can be placed to are really starting to push the boundaries of what a lithium battery is capable of doing. For instance, in the new electric vehicles that are being designed by Tesla, they use Panasonic lithium-ion batteries. But because they feature significant order 3-hour car charge times, there's a significant question of range anxiety. If, for instance, these lithium-ion batteries could be charged up to full in around 20 minutes, there would be no such problem, and the market for these electric vehicles would be much greater. In a lithium-ion battery, at the anode, lithium must be intercalated into a graphitic compound. Then, on discharge, these lithium ions enter the solution, and an electron can be captured by the cell and transported out. What powers this transition is the carbon material that is being used. So graphite is the currently accepted standard for such things.
So as Megan just mentioned, in commercial batteries, the current technology for anode material is graphite or some form of graphitic material. So essentially a ring of carbon atoms stacked one on top of each other. And what makes graphite useful as an anode is that it can store lithium and as such can have some sort of energy capacity. And it is conductive, which is important so that internal losses due to resistance are minimized. However, a major setback to graphite is that since it is a fairly bulk material, the available sites for lithium loading are restricted to its outer surface. And as such, there's a low usable surface area. To increase the total battery capacity, we will thus require more of these cells, which is bulkier, costlier, and it generates more heat. The proposed solution to this challenge is a carbon nanotube aerogel that we would look to replace the graphitic anode for commercial batteries. For those unaware of what an aerogel is, it is a 3D mesh of fibers that forms a porous structure. This structure has low density and very high mechanical strength, which is good for stability in batteries. Similar to graphite, it stores lithium. They are both made of carbon, and so the battery chemistry essentially stays the same. And a significant improvement over that of graphite is that its available surface area is significantly greater due to its porosity. Lithium ions are now able to permeate into the structure and can intercalate with the carbon on the inside. As seen from this table here, the available surface area of graphite, as determined by BET, is around 3, whereas that of multi-walled carbon nanotubes is significantly greater at 272. And we believe that with a higher surface area, that will improve the charge rate of batteries as more lithium ions can be quickly and readily intercalated into the anode material.
We converted our set parameters of wanting to compete with on the same footing as commercial lithium-ion batteries by saying that we wanted to exceed their charge time, so that is to charge more quickly for the same amount of capacity. So 45 minutes or less to recharge to 70% or more of the cell's total capacity. We also wanted a specific maximum charge of 0.075 amp hours per gram, because having energy on demand should also be backed up by being able to fill the same niches that lithium-ion batteries currently do. Secondarily, we wanted to prove with our prototype that we could achieve electrical durability of greater than 85% over 10 cycles, reasoning that this significant fall off in electrical capacity would show that the structures were not electrochemically stable within the cell environment. And we wanted an ambient charge leakage of less than 5%, demonstrating that the anode was doing its job of chemically storing energy as opposed to just plating charge into the cell electrically. Finally, we set some tertiary goals related to the operation of the cell in, for instance, a vehicular application.
And so now I'll quickly cover the fabrication process that we went through to fabricate our aerogel. This procedure was followed based off of a scientific paper by Brining titled Carbon Nanotube Aerogel. In this paper, Brining used single-walled carbon nanotubes to make their aerogel structure. However, for our design, we went with multi-walled carbon nanotubes due to the improved conductivity of this material. So initially, multi-walled carbon nanotubes are added to water to a 1% weight fraction, or essentially 10 milligrams of nanotube to 1 milliliter of water. Surfactant, in this case sodium dodecyl benzene sulfonate, is included, and the suspension is sonicated to form the gel-like structure. At this point in the procedure, the hydrogel is to be soaked in a water bath for 3 to 5 days to rinse out the surfactant and maintain solely the carbon nanotube structure. However, when we carried out this step in the procedure, we found that the multi-walled carbon nanotubes did not retain its structure and immediately collapsed. And so ulterior methods were required for the formation of the aerogel. So instead of letting it soak and removing the surfactant, the hydrogel was immediately freeze-dried or lyophilized to remove the water medium. However, as I mentioned, since no step was taken to remove the surfactant remained within the aerogel structure. And if we look at SEM, or scanning electron microscopy images, we do see fiber-like bundles that are representative of a gel-like structure. However, what we also see is charging at the edges of these carbon nanotube fibers, which is indicative of an insulating material. We know that multi-walled carbon nanotubes are conductive, and so this must be a thick coating of surfactant that has enveloped these fibers, which is unfortunate due to the limiting of the conductivity of this material, as well as the reduction of available sites for lithium loading.
We then fabricated these aerogel anodes into a coin cell, a 3 volt standard lithium-ion battery coin cell. So all other components of the cell were standard, say the same polymer electrolyte, the same cathode where applicable. We built both half and full cells. In the half cells, lithium metal is directly pressed on as a cathode. This leads to a rather distinctive first discharge peak because the lithium metal is directly being ionized into solution and does not interact with the anode material, our aerogel, until the first charge cycle. In the full cells, we built with lithium cobalt oxide in the discharge state. And we see an appropriate voltage range for these cells. The aerogel anode had to be machine pressed in order to fit within the very tight space requirements of the 3 volt coin cell. Less than 1 millimeter is the spec in order to fit appropriately. This meant that only a few milligrams of our anode was used per cell. And also in the machine pressing and vacuum drying step to remove atmospheric moisture, it is possible that the aerogel that we actually built with could have varied slightly from the aerogel characterized earlier in Chris's slides. Our data for the first half cell, you can see on the left. As discussed, that first charge peak is not representative, but the subsequent charging shows a very clean charge profile, no extra humps or spikes that would indicate extra electrochemical reactions going on. Furthermore, the shape of the charge profile does deviate significantly over the 10 cycles shown. Therefore, our material is pretty electrochemically resistant and is clearly doing its job. We used a constant charge, constant discharge method as opposed to a constant charge, constant voltage method, which would smooth out the beginning and end of these cycles, and a 5-minute rest period in between both charging and discharging. For the very first charge-discharge cycle, the capacity versus potential is plotted. This capacity is much lower than we had hoped. While we had exceeded, in fact, our criteria for charge time, we were able to charge up to 75% of 2 volts within 40 minutes as opposed to 45. So we are pushing and ultimately succeeding at bettering commercial technology. Our capacity is much lower than a standard lithium-ion battery 3-volt cell. This secondary data used by comparing both the charge and discharge capacity for efficiency and plotting it as a function of cycle shows a limited but fall off in terms of charge capacity for the cycle ID. You can see that the discharge capacity falls off faster. This is again a function of the residual lithium from the charge state half cell build. And the efficiency over 100%. Again, there's certain lithium that is just being plated onto the walls due to it being built in excess. For our full cell, with the lithium cobalt oxide, we've now looked at cycles around 9 to 21, so significantly further down the cell's lifetime, and you can see some degradation in the charge profile. There is definitely less capacity by cycle 21. The same charge profile was applied, so 5 minutes rests and 20 microamp charge discharge. The efficiency numbers are in the mid to low 90s. This is acceptable. These are not quantum efficiencies, but rather include internal resistance. And the fade in discharge and charge capacity is significant at first, but beginning to level off. So perhaps over 100, 200 cycles, it could be expected that the charge capacity would not significantly drop from here. Both our half cells in series and our full cells are able to power a small 2 volt, 10 microamp LED, although as noted, because of the low charge capacity, we can't sustain that for very long. So in conclusion, because of our fabrication method, our hydrogelation step was unsuccessful. This meant that the surfactant rinse was not possible. The surfactant carried over into the aerogel structure after freeze drying and resulted in a lower surface area and lower conductivity material. This resulted in lower maximum capacity when we actually look at our battery's cell parameters, but the charging time remains appropriate. This leads us to believe that this technology has significant potential and could be commercialized if the significant issues in increasing capacity can be resolved.
So in terms of future research, there's a fairly clear path. One of the major issues as seen in the SEM images is that the presence of surfactant really inhibits conductivity and maximum charge capacity. And so improving or developing ulterior methods for fabrication of the aerogel is imperative for improvement in the electrical properties. Some methods to do so would be to determine or optimize the best ratio of surfactant to carbon nanotube used in fabricating the hydrogel. Otherwise, in Brining's paper, it is known that single-walled nanotubes can effectively make an aerogel. It is possible that by incorporating multi-walled carbon nanotubes, we can form a hybrid such that a good structure is formed with good conductivity parameters. Finally, it is also possible to investigate the functionalization of multi-walled carbon nanotubes to promote self-adherence through cross-linking or some other form of chemical process. In terms of improving the characteristics of the fabricated coin cell, we can look at optimizing the lithium loading capacity of the coin cell such that the energy capacity per gram of material is improved, which will lead to less waste and a lighter product. Multi-walled carbon nanotubes, as mentioned, have a lower conductivity than that of graphite, and to improve that, a potential method could be applying a metal coating around the aerogel to improve electrical contact. Here are references used in this project, available upon request.
And we'd like to acknowledge the significant help provided to us by the nanotechnology undergraduate laboratories that allowed us to carry out the synthesis ourselves and resulted in a functional aerogel. And the time and expertise and lab space provided by Professor Aiping Yu and her graduate research assistant Kun Feng, without whose help the cell testing and fabrication would never have been possible. Could we open the floor to any questions?
Those were numbers obtained from literature, and you're correct. Then there are a lot of different parameters that will alter the surface area as reported by BET, namely the size and makeup of the multi-walled carbon nanotube. However, we believe that the surface area for graphite should be fairly consistent, since it is a bulk material at around 3 meters squared per gram. In fact, the multi-walled carbon nanotubes that we used for our fabrication were reported to have a specific surface area of 60 meters squared per gram. So while we may not be able to achieve the 272 as reported by literature, there's still a 20-fold improvement in surface area for our nanotubes.
But you know that theoretically graphene should have the highest, right?
Yes, work on graphene.
I don't think graphene is used extensively in lithium-ion cells of high capacity because while it has high surface area, structuring it into batteries is more of a problem. Again, it's very thin, right? I think the general material used, especially in vehicular applications, is graphitic. So not single film graphene, but rather thicker multi-layer pieces.
Other questions? All right, let's thank them again.
Oh.